and you know the strength of this, sorry, you sit there, so I can't look you separately. I want to look all, so you can, next lecture you can shift it. So if you have a neutron source, so this is the problem for the life, huh? There is a neutron source here, and around there are some animal or the people, so that the rate of the change of the neutron source, you know already, the rate of the decay. So you want to know that after how many meter, how many time, how long it will take that the fall, for example, the whole area of 1 kilometer be dominated by the nuclear radiation. So again, these are question works. In the reactor, in everything, it works like that. So this is the question. And normally, you know, I told you for a steady state, when you consider the change of the temperature not very high, or if you wait very long time, you can forget about that. And if you consider even no source, that's very important. STD and source-free and look, STD means that partial derivative of this thing. Source-free means that forget about the S, huh? Forget about the source, forget about the time change in the temperature, and also forget about the density and uniform density. Even for uniform material, still you cannot say that it's easy to find the temperature. You need to solve this equation, huh? If you relax all the conditions, still you need to solve very complicated equations, Laplace equations. Yes? And it is not trivial that if somebody say that I have a source, I don't have the source, I will accept the source, and you know what does it mean? For example, this neutron source, for example, started the decay now, and you are standing 1 kilometer from the source, and you don't see the source, so you feel that the source is ended already. And 1 day after that also, huh? So long time passed. So you can be sure that, okay, time is not important. Relax that, and the source relax that. And also you say that, okay, the density of the environment or nature doesn't change it from year to year, huh? I mean, you don't go to the mountain to have a difference of the pressure or something. The matter is the same. The matter feel at 1 kilometer. Still, in that case, you cannot be sure that you will get some radiation or not, because you need to solve this equation. So this equation gives you the rate of the radiation. So I will spend a lot of time to solve this equation for you for different geometry. So let me to stop it, but I needed to one more things, because this sequence doesn't finish. I told you I started from the normal calculus. Very quickly I run to the generalize that to the multivariable. So I started from the three-dimensional, one-dimensional normal R, huh? df dx. R, just real number. After that I pass it to R cubic, huh? Euclidean. And I get gradient. Or after that I find that it should be something like divergence vector. After that I pass it to divergence gradient of the somethings. But the other direction. The other direction is that I told you there is another possibility to have this expression also. Yes? If you want to handle such a question, you need to understand one thing, that this operator will act over both of them. Huh? It's not easy that just take it over that or take it over that. So I want to open that, and how I can do that? I name it this vector C, okay? So now C looks like for me like this. Huh? So this is a vector, and this is a vector. And I already explained to you that the I component of this vector is that. Huh? And what is the A car? A car is F V car. F V car. So just follow what I'm writing. So I wanted to show you something interesting. So now it's going to make the derivative from both of these objects, f and v. So as usual, you know that the differential of the two functions are differential of the first one multiplied to the second one plus second one multiplied to the first one. Epsilon ij k, partial derivative of s. So and this is out of business first. I write the line like that. This derivative doesn't work for that. It works only for f. And the next notation is, now it's out of our business, and we have this. Yes? This is the very useful notation. Okay. How I can write this expression? I can write ijk. What is this? This is a gradient f component j. Vk plus f epsilon ijk. No. Be careful. Can you tell me what's that? This is exactly epsilon ijk, aj bk. So this is the I component of cross product of these two. Look at that, what I write here, what I write here. Maybe not in the first looking, but you will see. Plus f, what is that? Yeah, this is a cross product of this object to this object. So I find this expression, curl FV, I use it the word, but I will use later. Gradient f multiplied to f is. This is a new object. Call it curl or rotation. You have a vector, so for vector only the change in the coordinate is not important. Sometimes it's important to see that is it the direction of the vector changing or no? And this information about the direction is here. You remember the divergence was related to the flux, del dot v. Del cross v is related to the rotation of the water fluid. So I can use a model, I can make a model for you like the model which I make to understand the meaning of divergence. It was a fluid passed from the cube. I can make a model for the circulating water or fluid, and I can show that the flux here is not passed from the volume. It's the flux which passed from the plane here, a surface plane right here. And this is related to the, this. The amount of the fluid which passed from this, for example, narrow, is related to the rotation. So I want just to write the old one. This we call it curl. Curl is a vector. Fv is gradient f multiplied to v plus f curl v. That's. So you remember what I told you about the source-free vectors. The vector with divergence of v is 0. We have a irrotational fluids or curl-free. You can have the fluids which we call it irrotational fluid. So that's the end of the today. Just I want to give you the title of that. So irrotational fluid vector fields are the vector which curl v is 0. So you get two things. Divergence of v is 0, I call it source free, And this is called, I call it this irrotational. you need to know that still there is no solution for the equation of the fluid which is irrotational and the source free. We cannot find the form of the fluid. There is a equation called a Navier-Stokes equation. You remember how I find for you the heat temperature equation? So similar to that, a little different, you can use from the different statements like Bernoulli principle and something like that. You can get an equation like that, but very complicated then. And you have this term here, and you will have this term here, and you will have V to this, V to that, nonlinear terms. Even if you consider irrotational and the source free, there is no solution for that. So this is one of the questions which still remain unsolved. Find the profile of the fluid when the fluid is irrotational and the source free. But you have a density, so you cannot forget. So, but I want to mention one thing, because I never will back to that. Next lecture I will talk about a theorem called Helmholtz theorem. Helmholtz theorem say that if you have the source, and if you give me the curve, I will give you the vector unique. So I want to tell you that some more identity, you need to go and find it. For example, curl gradient anything is 0. Divergence curl any vector is these two equations. What is the way? The way is the strategy which I used to prove, so you can use that. So curl gradient of anything is 0, and divergence curl anything. So I will stop at this here. So next lecture I will talk about something remain from this subject. So I want to back to this vector and try to give the idea of the Helmholtz theorem. So that's all. Thank you.